Yo, 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 welcome to Acid and Base, Nomenclature and pH.
Okay, turn to page 130. We're going to start off with naming binary acids.
So, a binary acid is just an H hydrogen with one other element. So, I want you guys to write that above where you guys see naming binary acids on your graphic organizer. H plus one other element. So the naming rules you guys can see matches with the number of boxes there. So we're going to write down begin with hydro in the first box, and then use the root of the element name, and then add the suffix ic. And in this last box, I want you guys to write down the example. So HCl is hydro, chlor, and that's the root of the element chlorine. And then we take that ending and change it to ic, and we add acid. So hydrochloric acid. Let's name these binary acids. So I see I have Br with H, so it is binary. So the name starts with hydro, using the rules from the previous slide. So hydro, brom, ic, acid. So hydrobromic acid. I see is iodine, so hydroiodic acid. And last but not least, fluorine. I take that root fluor, so hydrofluoric acid. There we have it. Okay, ternary acids. They're acids that have an H with a polyatomic ion. So that's what I want you guys to write down above where you see naming ternary acids, H plus polyatomic ion. The rest of the box corresponds to the box that you guys see here. Okay, let's begin. We start off with naming the polyatomic ion without the ending. Then we change or add the ending, a suffix, based on the ending of the polyatomic ion. So if it started with an 8, we change it to an ic. And if it started with an ite, we change it to an us. Okay, so let's take a look at our example. Our example is HNO3. So to name this acid, we start off by looking at the polyatomic ion. NO3 is nitrate. So I take the ending off. Since it's an 8, I'm going to replace it with an ic. So the name is nitric acid. There's a mnemonic device that will help you remember the ending or which ending to change it to. So the phrase is, I ate something icky that caused me to get gingivitis. Unique way to spell gingivitis, but again, we will remember it, right? Vitus, ate, icky, ick. Okay, I ate something icky that caused me to get gingivitis. Cool deal. Here's a list of the polyatomic ions that was in your first semester spiral. If you guys lost that spiral or can't locate that page, here it is again. These are the common ones we will see, and this will help us name acids. First step to naming ternary acids is to take a look at the polyatomic ion. ClO3 is a chlorate, so I take that 8 off, is chloric acid. PO3 is phosphite, so that I gingivitis, so I change it to phosphorus acid. And last but not least, y'all, CO3 is carbonate, so carbonate, carbonic acid. Naming bases. So bases are just cations and hydroxide. So I want you guys to write that down. Cation plus hydroxide. So to name it, y'all, we use the same rules as for the polyatomic ions. We name the cation as is, name the anion as is. And then our example is sodium hydroxide, NaOH, sodium. We didn't change it at all. Na, sodium, we just simply named the cation. Hydroxide, simply name the cation, again, calcium. Hydroxide, name the cation, potassium hydroxide. Pretty simple. Water can sometimes act as a bronzed-Lowry acid and sometimes as a bronzed-Lowry base. So this is called the self-ionization of water. So in your notes, please locate this area and you're going to write down this equation right in this location here, self-ionization of water.
So this is the self-ionization of water equation. Water plus water yields hydronium ion and hydroxide ion. So we have to determine which one is the bronzed-Lowry acid and the bronzed-Lowry base because water can sometimes act as both. Okay, so I take a look at my first substance and I try to determine what happens to it. So I see that for the first substance, it looks like the hydrogen was added to water. So this means that this water here gained a hydrogen or accepts. So an easy way to remember the Bronsted-Lowry definitions is to consider that acids and bases are bad. So base accepts the proton or the hydrogen, and then the acid donates or gives away a hydrogen. So I know that since there is a 3 here, it gained 1. The original number was 2, it gained 1. This is my Bronsted-Lowry base. Let's take a look at the other water. The other water looks like it lost a hydrogen or donated a hydrogen because there's only 1 hydrogen left where it started off with 2. So this water here would be considered my Bronsted-Lowry acid.
All solutions, like I said on the previous slide, have some hydrogen ion or HVO plus equivalent and some OH minus or hydroxide ion. So the definition I want you guys to write for the pH should be written here. pH is a measure of the concentration of hydrogen ions dissolved in solution. The equation, y'all, again, if you have room, write it small, right beneath that table, is pH equals negative log of the hydrogen ion. So this bracket, if it wasn't mentioned before, let's talk about it now. The bracket is considered to be concentration, okay, molarity. So these properties here, y'all, I want you guys to write it beneath the equation and write small because this room right here is going to be used to summarize something else. So make sure you guys make room. So low pH equals high hydrogen concentration, hydrogen ion concentration, and low hydroxide ion concentration. And the opposite is true. High pH means low hydrogen ion concentration and high hydroxide ion concentration. So I want you guys to write it below the equation. So this graphic that you guys see right here, y'all, can be found next to the box that says what is pH. So label as you guys see it. The left-hand side is pH is equal to 0. In the middle, pH is equal to 7. And on the right-hand side, pH is equal to 14. Be sure to label the region that between 0 and 7 is considered to be acid, between 7 and 14, base. And in the middle, y'all, neutral. Be sure to label this. This is not included in your graphic. So, if I were to take a look at a low pH somewhere around here, even at a low pH, y'all, there is still a small amount of hydrogen ion. And I want you guys to write that statement here. Even at a very low pH, there's still a small amount of hydroxide ion. Okay, we can see that there, the hydroxide ion. The majority of that would be in solution would be hydrogen ion, but there's still just a very small concentration of hydroxide ions. So I want you guys to write this statement that I just underlined beneath your table and above the self-ionization of water equation. Last but not least, y'all, we're taking our attention back to the what is pH box. I want you guys to label that table there. You have 4 spaces for these 4 things. I'm going to underline it. Neutral, hydrogen ion, the equal sign there, and the hydroxide ion. So be sure to label it. Neutral means that the concentration of hydrogen ion is equal to the concentration of hydroxide ion, just as we saw on the previous slide with the graphic. In the middle, there is equal amounts. Then, with acidic, we know that there are more hydrogen ion concentration than the concentration of hydroxide ion. Remember, even at a low pH, there's still some hydroxide ions in solution. The same is true for basic with hydrogen ions. So we know that for a basic solution, there are more hydroxide ions than hydrogen ions, but nonetheless, hydrogen ions are present. So underneath the low pH, high pH statements, I want you guys to copy these statements down. Acidic solutions contain small amounts of hydroxide ions, while basic solutions contain small amounts of hydrogen ions. Okay, y'all, that is it for today. Be sure to practice the naming rules for acids and bases. So, have a good one.